Hello everyone, we will continue our discussion on this change of measure idea. Just recall from the previous lecture the basic ideas that we started when we are introducing this risk neutral pricing in continuous time, that we have a probability space on which we have a Brownian motion, and we want to define a new probability measure which is equivalent to this, which is P tilde of A, which we defined as given here in this expression, and with that Z we can define a process Zt which is the Rn derivative process, or Z is what is Rn derivative. Now for any y which is Ft measurable for any fixed t between 0 and capital T, we have these two lemmas, which is what is basically just the continuous time version of what we have seen in the discrete time model, right. So, that is what we have seen. Just recall all these points. So, whatever we have written down here, these two lemmas and the ideas of how to be define P tilde of A and Zt, Z, and what are the properties of this Z. With these properties of Z, of course, these two are equivalent. P and P tilde are equivalent probability measure, which we know by what does that mean? It means that they agree on what is possible and what is impossible, means agree on sets of probability 0 and conversely sets on probability 1 as well, right. Now, keeping this in mind, with these two lemma in mind, now let us state the Girsanov theorem, which is going to play a major role while we continue forward our the continuous time finance models. Okay. Now, what do we have here? Okay. So, you have a Brownian motion. Okay. Now, we are be a Brownian motion on a probability space, say omega f p, and this is, and let f t is also in this be a filtration for this Brownian motion. Again, it has the properties that we have defined when we say filtration for the Brownian motion. Okay. Now, what we do is that we will pick, okay, a real number, let theta belongs to R, okay, and define the process Zt as e to the power minus theta times Wt minus half theta square t, and another process W tilde t, which is W plus theta times t, is what this process is. Okay. We may also assume some conditions for under when we actually try to prove this, but that we will not state as part of the result. So, here what we have picked? We have picked a real number theta. This, the same process, the way of defining could be generalized even if theta is a time dependent quantity, but non-random, or even to the case where theta is an adapted process. Okay. But for our purpose, since theta constant would do the purpose for our discussion, so we will restrict the statement of the theorem or the theorem itself to the constant theta case. Now, what we do? Set Z to be Z capital T, then you can see that expectation of Z is 1, and also probability of Z greater than 0 is also equal to 1, and under P tilde, right, given by say, suppose if I want to give a name to this, let me give this as this red star, okay, given by this, okay, the process which is W tilde t is a Brownian motion, right. This is the main result of this. So, what you do? You have a Brownian motion defined on a probability space endowed with a filtration f t. You pick a theta, you define this z t and W tilde t's, then you pick this z to use a new probability measure p tilde, and under that probability measure p tilde, this W tilde process, which is what? It is basically W t plus theta t. Recall W t, if I simply look at the distribution, it is normal 0 t. Now, what we are doing? We are shifting this W t, right, by. So, this is basically a Brownian motion with drift process. Okay. Now, this drift one, by adjusting the probabilities, you are bringing back to W tilde t will be again normal 0 t under a different probability measure p tilde. Now, how to get that p tilde is what this process describes. So, how to get an z and so on. Okay. Let us quickly go through the proof, though it is in our discussion for finance this may not be relevant, but this is simple and this you must understand that how this is coming. Okay. Now, how do we show that some process is a Brownian motion? Okay. We will use the Levy's criteria. Levy's criteria, which means a continuous time martingale starting at 0, having continuous paths, having quadratic variation 1 per unit of time is the Brownian motion. That is precisely that what we will see. Okay. So, the process, one can easily see this process, okay, this is starts at 0, right, because at time 0 W 0 is 0, this is also 0. So, this starts at 0 and has continuous paths as well. Okay, that is easier to see. Okay. And next, this is one part. Next part is also pretty simple, that if I look at the quadratic variation of W tilde would be same as the quadratic variation of W, which is equal to T. You can easily write down in terms of stochastic differential of this W tilde, and you can compute and see that this is actually the case. Okay. So, this part is also clear. Next, what we say is to show, next what we are going to look at is that to show, what is remaining to show, that this is a, since this is a martingale under p tilde. So, we want to show that this is a p tilde martingale. If we show this, then we are done, right, because by Levy's criteria, then such a process, right. So, this has continuous paths, quadratic equation. Now, next to show that this is what it is required. So, this is what we need to show that this is actually the case. Now, first thing that you can observe is that how do we show is what the following. Observe that Z t, the way we have defined, is a p martingale, right. You go back and see this the expression for this Z, we have written this is for recall for a sigma a constant e to the power sigma w t minus half sigma square t we have written. So, sigma now you can assume this as simply as minus theta, right, it is also a real number. And so, this expression is actually what we called earlier the exponential martingale, that is what is occurring here. This is a martingale under the measure in under which W is a Brownian motion, which is P. So, this is a P martingale, you can easily see, right. Otherwise, another way to see that is that if you use Ito's formula, what you would get is that if you compute the stochastic differential, this will be equal to this quantity. So, this also tells us, sorry, theta t nahi, there is only theta here, right, theta is a t, twt. This also tells us that this is nothing but if you the Ito integral component, there is no dt term in the expression for stochastic exponential, and hence this is a pure Ito integral. The right hand side is also a pure Ito integral, and Ito integrals are martingale, and hence Z is a martingale. You can easily see this basically, that is what you can also see by this as well, by looking at the form of this Z Z T, where which if it does not have Z T terms, right. So, you can write this as Z T as Z naught minus theta times say 0 to T Z u d w u. So, this is a martingale constant times minus or plus whatever is the case, this is a addition of a constant. So, this is a martingale. So, by this also you can see that this is what is true. So, in particular what we have in particular our expectation of Z, which is expectation of Z at capital T, since this is a martingale, martingales have constant expectation. So, this is across all time points, this is true, which is equal to Z naught, which is equal to 1. Okay. So, we then have what we have, because Z t is a martingale under P and Z equal to this, we have Z t, which is expectation of Z capital T given F t, right, which is expectation of Z this, right. So, this Z is nothing but this quantity Z t's, right. So, what do we have? Then Z t that we have defined there is actually what is the Rn derivative process. Okay. So, that implies or this shows that Z t is Rn Radon-Nikodym derivative process, okay. And hence the lemma, two lemmas that we have seen, lemma A, lemma B, applies to this particular scenario, where to this is a t, when if we pick any random variable, then we can do that computation. Okay. So, really we just have to use that computation to see that what we are aiming to get. Okay. So, next what we will show? We will show this is we have observed this. Now, we will show that this process is a P martingale. So, how do we see? Look at this, which is W tilde t d Z t plus Z t d W tilde t plus d W tilde t d Z t, right. This is by the Ito's product rule, what we can write is this. Now, we just have to plug it the values for each of those, okay, minus tilde t theta z t dwt plus z t dwt plus z t theta dt plus these two quantities dwt plus theta dt, which is dw tilde, and minus theta z t dwt. Okay. So, now if I simplify this, so what you would get is minus w tilde t times theta plus 1 times zt dwt. So, what will happen to the other term? This third term and this fourth term that we have written on the right hand side will get cancelled, right. So, this term and this term will get cancelled, and dt dwt is 0, dwt will give you this. So, that is minus theta zt plus theta zt get cancelled. So, you will end up with this, and hence this is what is here, which implies that this implies, right, your w tilde t z t is p martingale. This is the next step of this proof. Now, you pick two time points s less than or equal to t less than or equal to capital T. Now, lemma 2, lemma what you read A B we have written. So, the lemma B and the P martingale property of this process w tilde t z t imply the following. What we wanted to show? We wanted to see that this is what it is. This we know 1 by Zs E of w tilde t Zt given Fs. This is exactly using the lemma B. Now, we know that this property w tilde Z is actually a P martingale. So, this means this is equal to w tilde S is at S, which is equal to w tilde S, which implies w tilde T is a P tilde martingale, and hence w tilde T is a Brownian motion under P tilde, the P tilde that we have defined here. Hence the proof, right. So, this is what is the Girsanov theorem, which we will be using a lot whenever we want to make or construct the probability measures and so on. Okay. So, with this tool in hand, now we can actually go to the continuous time model, which we call as BSM model, which we have seen in some way that if you take a limit of the binomial model, what you end up with is a geometric Brownian motion model, and that is what we will have in this BSM model. All the assumptions that we had with respect to the market in the discrete time model, in the binomial model case, are also holds true here. Those are except the evolution of risk free and risky assets, because that is what is the time, continuous time and discrete time model differs. All other assumptions is true, which means there is no bid ask spread, there is lending rate and borrowing rate is the same, and any asset is available to be bought or sold at any amount of those assets are possible. So, all those assumptions which we generally put under the name frictionless market, right, is true even in the case of this. So, what is difference is only the evolution of the risky and risk free assets which we give now. Okay. So, what we have? So, we have the underlying Wt. So, it is basically 0 to t is the interval in which we are looking at it. So, this be a Brownian motion on a probability space omega f p, and let f t be a filtration for this Brownian motion. Okay. The simplest case is that take this Brownian this filtration to be the one generated by the Brownian motion itself, because that is what we will going to assume when we go forward. But it could be in general. If it is in general, then this needs to satisfy the condition for being a filtration for this Brownian motion. Okay. Now, so consider a stock price process whose differential is given by, or the dynamics is given by dst equal to alpha st dt plus sigma st dwt. We will generally assume sigma to be a strictly greater than 0 quantity, right, but we need to assume that it is non-zero. For all the analysis purpose, we need to assume that this is non-zero, but it is in general it is greater than 0. Requirement is this, but actually this is greater than 0 in practice. Okay. But for the analysis purpose, this non-zero thing will suffice. Okay. So, here what is alpha, what is sigma? We have already seen this is the mean rate of return, and how this is interpreted as mean rate of return we have seen, and sigma is the volatility. Okay. In general, again alpha and sigma could be a time dependent quantities, or it could even generally be adapted process, but again for our purpose, since we have this GBM in mind, so what we have is this process are equivalent. What does this means? This means that my ST is given by this process, that is all it is, right, e to the power sigma Wt plus alpha minus half sigma square times t. This is what we are saying, right. So, when we say either differential form or in this explicit form, what we mean one and the same, right. So, this is the second line. So, this is what is basically the geometric Brownian motion which we call, and we obtained this as a limit of a properly scaled binomial asset pricing model. So, that is what it is here. So, instead of giving an expression for ST, we are writing its dynamics of ST, and that is typical way of doing here. So, this is about the stock price process. Then the risk free asset, this is risky. Stock price in general, essentially the risky asset is what then we are looking at it. Then there is a risk free asset its dynamics is given by, you can write it as dBt as rBt dt with typically B naught equal to 1, or equivalently Bt as in general B naught e to the power RT, which with B naught equal to 1, this is e to the power RT. Okay. This is, you can say, assume this is a bond, okay, say bond or money market. Just imagine that these are the case that we are have in mind. So, this is the dynamics is given by this. okay, or equivalently Bt is given by this vector, which is what we call Degrowth. Sometimes or equivalently we can also write this in terms of the discount factor, which is minus R dt, right. So, which is essentially dt is e to the power minus RT. So, instead of writing this is 1 over Bt, essentially it is 1 over Bt. If you apply the it was formula to that function 1 over Bt, you will get this expression, does not matter. So, this is second one is in sometimes convenient to look at the discount factor rather than the growth factor only in that sense. So, what we have two dynamics, one for the risky asset and one for the risk free asset. So, in binomial model how the price evolves from one time to the other time is given by the binomial model, in this case by these two quantities, that is the difference. Okay. Now, once we have this, you can see that in the risky assets, the stock price dynamics has a dW term, whereas the risk free as a bonds dynamics has no dW term, and you see that bonds dynamics Bt is simply e to the power RT, which is what we associate to the risk free asset, because there is nothing random there, and St which has a Wt which has a quadratic variation property, right, which means it is random with a positive quadratic variation, that is what is. So, that is where it is more random. So, at any given point of time in any dynamics, say this is predictable in some sense, but this is in a way more random or purely random in that particular, in this particular example case. Okay. Now, once we have this, now we can look at the discounted stock price process, which is d e to the power minus RTST, which we have already obtained in the earlier BSM equation derivation, right, or you can simply apply Ito's formula again to arrive at this expression, which we are reproducing. Again, what we see is essentially the mean rate of return when you discount the stock price process by the rate R, by the mean rate R, the mean rate of the asset S is reduced by the rate R. So, it becomes alpha minus R. So, this is what we have observed, this is what we could see here also, here as well. Okay. Now, this can be written as sigma times e to the power minus RT times ST times some theta times dt plus dWt, right, where what is our theta? Theta is alpha minus R by sigma, which we call it as the market price of risk. Okay. So, what does this mean? People who are aware, this will also be called as Sharpe ratio if you wanted to say, but this is more appropriate here. We did give this name market price of risk. So, alpha is the mean return of the risky asset, alpha minus R is the risk excess return over the risk free asset, and sigma is the volatility, which is we call risky, a measure of risk. So, per unit of risk, what is the excess return that you get in risky asset is what is called the market price of risk, and this is what this theta is. Okay. Now, if if we write it for this particular theta, okay, now we can see that we can create a Brownian motion, okay, say W tilde, right, and with that we can write this process as dW tilde t. Okay. So, how do we get from here to here? We are using Girsanov. So, recall Girsanov mein kya, what we have to do? that we pick a theta, define an zt and use that zt to reach z, and from z you will define a p tilde, and under p tilde, right, this process, this theta times t plus wt process would be a Brownian motion, and that is what we call as dw tilde. So, this is a Brownian motion which by Girsanov, by appealing to Girsanov we see that with this theta, with theta as above means in this particular case this is the theta that we have here in mind. Okay. With this particular theta you supply in Girsanov, you get a p tilde, z and w tilde, and this is that w tilde that you get here. Okay. So, this is what then you see. So, what does that mean? This means that this process, the discounted stock price process, is a p tilde martingale, right. This is a p tilde martingale, that is what this expression means. Okay. Now, you would see that you can derive this is you define this p tilde is what we call it as the risk neutral measure, risk neutral probability measure, risk neutral measure. So, what does this? So, what are the properties that it should have? It should have two properties. One is A, P and P tilde are equivalent, and B, it makes this one e to the power minus RTST is p tilde martingale. If it makes this discounted asset price process as a martingale, and if it is equivalent to P, any probability measure which is equivalent to P and which makes the discounted asset price processes as martingale. In this actually there are two assets, risky and risk free, but risk free asset, if you look at it, it is e to the power minus e to the power, if you discount by that it becomes just 1. So, it becomes a constant value. So, you look at only the risky asset which is e to the power minus RTST. If this is a p tilde martingale, then that measure is what you call it as the risk neutral probability measure or risk neutral measure. Okay. Recall, now you can make a connection to this discrete time model what we have done. In discrete time model we define p tilde by using the parameters of the binomial model, which are actually u, d and r. So, we define p tilde and q tilde which make up the risk neutral probability measure by defining using these quantities, by defining them using those parameters. Here also we are actually using the parameters of the model to define a new probability measure, but it is in a much more complex way. It's in the underneath, like the description it is coming, because here we cannot define for each one of those paths or anything, each one of those elements in an uncountable probability space. So, we define for each set A using this Rn derivative, right. There it is simply ratio, here it is actually an Rn derivative which is a continuous process, and hence things are involved, that is the only thing, but we are doing the same thing. You see theta we are taking alpha, r, sigma, these are all the parameters of the model, alpha, r, sigma, all of them are coming from the model to make up this theta. Theta you supply in Girsanov to get p tilde and w tilde. So, that p tilde is what your risk neutral probability measure, right. So, that is what. So, what are these properties? It should satisfy these two properties. Later we will define more precisely, but this is what you have here. Okay. Now, if you look at the discounted price process is a p tilde martingale. So, what is happening to the undiscounted price processes? Okay. So, this undiscounted price process under p tilde, what is its dynamics? Okay. We said dst. Okay. So, we have seen this dst as alpha times st dt plus sigma times st dwt. Okay. Okay. Now, dWt you substitute in terms of dW tilde. So, what you would get, right. So, which is alpha times St dt plus sigma times St. dWt is actually dW tilde minus theta times dt, right. So, this is dW tilde t minus theta times dt, and now theta is alpha minus r by sigma, right. Sigma and this sigma will get cancelled. So, it will be alpha minus r, I mean theta. So, it is minus alpha plus r. So, that will go. So, ending up with r St dt plus sigma St d W tilde t, right, or St equal to S naught e to the power sigma W tilde t plus r minus half sigma square times t is a solution to this SDE, right. So, what is happening here? dSt is essentially this quantity. You look at this, what happens under W tilde, okay, and you also look at this sigma, right. So, look at this under W, St has a mean rate of return alpha and a volatility sigma. Under W tilde or under P tilde, right, this stock price process has a mean rate of return R and volatility the same sigma, right. So, now you can see, like when you discount this by R, this first term goes away, leaving out with only the dW term, which makes that as a martingale, right. So, that is what you see here. Okay. So, this is what happens to the undiscounted stock price process under P tilde, right. So, what is its mean rate of return? It is R instead of alpha. So, it changes the mean rate of return to R. So, how does it is being done? So, this is in some way similar to what happened in the binomial tree. What is changed? Binomial tree, like it did not change the probability, it did not change the, when it changed from P to P tilde in the binomial tree, what we had, it just changed the probabilities of that, but it did not change the up and down movements, which is in a way similar here, that volatility term is what is basically the which stock price paths are possible or not possible. So, it keeps the same, only thing is it changes the mean rate of return. Whenever this alpha is greater than R, which is typically the case, right, normal times that is what you expect a risky asset to give more rate of return than the risk free asset. Right. What it does is it changes the probabilities by assigning higher probabilities to those paths which have which have lower return, so that the mean rate of return becomes or downs to R rather than alpha. That is what is happening here, right. So, now once having seen this, now we will look at the value of portfolio or portfolio value process under P tilde. So, this part is, this is S stock under P tilde. What happens? Now, this is what we have observed. Now, we look at the portfolio process that we have. Recall, what is the portfolio process that you have? So, you start with an initial x naught and at each time hold delta t positions in stock. Okay. Investing and borrowing in risk free as required. So, this is what is the portfolio position delta t at each time t, hold this much position in stock. So, the rest is in risk free. So, if you look at a self financing portfolio process of such nature, then what is the dynamics that we have seen? We have again already defined or already derived this. Okay. So, maybe I can start the first line itself. So, which is basically delta t dst plus r xt minus delta t st dt, right. This is what we have written earlier. We have also shown that this is equal to, by one or two steps, if you write r xt dt plus delta t alpha minus r st dt plus delta t sigma st dwt, okay, which you can show, or which could be written in this particular form, that my r xt dt plus I can write this delta t sigma st times theta times dt plus dwt with the same theta as earlier, right, with the same theta as earlier. Now, if I look at now Ito's or the discounted value of this, which is also again we have obtained earlier, which will be equal to, so this first term will go, because that is what is the effect of that, the other terms will be there. So, that means that my delta t sigma e to the power minus r t s t theta dt plus dwt, right, which can also be seen to be delta t d e to the power minus r t s t, which means the evolution changes in the discounted value of the portfolio entirely due to the fluctuations in the discounted value of the underlying stock multiplied by the position, right. This we can use the earlier quantity, and we can write this as sigma e to the power minus r t s t dw tilde t. So, what we have now, this quantity e to the power minus r t x t is p tilde martingale, right, that is what we have. So, what you have in front of you for investment, that there is a money market account with rate of return r, and there is a stock, okay, with a mean rate of return r under p tilde, okay, regardless of now how you invest. So, the mean rate of return for the portfolio is going to be r under p tilde, which means your proportion of the investment that you decide between risky and risk free is does not matter, because the portfolio is going to give you a rate of return of r. Recall exactly same thing we have seen in the discrete time model, binomial model as well. So, that is precisely, so that is what we said, understanding there is much easier. Here we just have to put the things in the proper framework of continuous time model. Other than that, everything is the same here. Now, we will compute the pricing aspects, pricing under p tilde or under the risk neutral or measure or risk neutral pricing formula. So, what we have, recall when we started this discussion, we took the European call option as a derivative, and we obtained the Black-Scholes Merton PDE along with the terminal condition, solving which we got the BSM formula. Now let us look at a generic European type derivative which is Vt, right, which is what an European derivative with maturity capital T. And in our case, what does this mean? Well, this means that this is simply, technically what this means, this is simply is any Ft measurable random variable. That is what is Vt for us. Okay. We will not worry what is the form. If it is St minus k the positive part, it is European call option. If it is k minus St pass to the positive part, it is European put option. If it is simply St minus k, it is forward contract. Okay. So, you could have examples St minus k, k minus St positive, St minus k, right, St to the power some m for m greater than 0 or m integer, whatever you want to say, right. You have log of St, right. So, you have any function which is a function of St, these are all path independent. Okay. Again, you could have path dependent, you could have anything is what we say is an European derivative with maturity T. Just like in discrete time, all these functions could be framed into this. So, right. So, we allow this could also be a path dependent, something like max of Su for u lies between this, all these things. So, these are all could be path dependent, path independent, everything. Okay. Now, what we wanted to know? We want to know an x naught, we want to know an x naught and a portfolio process delta t. Okay. So, we wish to know what is the initial capital required and what is the portfolio process that he needs to adapt to set up a short hedge, means short position that he is taking the underlying derivative. He needs to set up this hedge, which is what we call short hedge, to set up the short hedge, that is to meet what I should have x t equal to V t almost surely. Okay. That is what we need. If it is surely, it is done fine, but in continuous time we always require this to be almost surely case. So, with probability 1, if I can achieve V t by replicating this, by using this delta hedging strategy delta t and starting with some initial wealth x naught, that is what you call, you need to know. Okay. So, he wants to do this. So, in a moment little later we will see that this delta t, whether there exists such a delta t. Okay, we need to be assured of that will be answered little later. For the moment you assume that there is some delta t that is available, then x naught and is what you need to know to set up the hedge. Okay. So, this can be done if you see. Now, once you could have, so there exists, assume there exists such a delta t process. Okay. Now, if that is the case, if that can be chosen, okay, now what we see, this fact that we just now saw, that e to the power minus r t x t is p tilde martingale, p tilde martingale. So, what does this means? So, this means the following, that since martingales have constant expectation, right. So, what this would mean is essentially e to the power minus r t x t is equal to e to the power minus r capital T x capital T given f t, right. So, this is what is the martingale property gives, right. Now, since we want this x t to replicate v t, this is also equal to e to the power minus r t v t given f t, right. Now, since x t is the value that is required at time t to hedge your position from small t until capital T, and hence this is the value of the derivative at time t, and hence you would call this as V t, right. So, what we have is essentially e to the power minus R t V t is e to the power minus R t V t given f t, or V t to be e tilde of e to the power minus R t minus t V capital T given f t. This is for all 0 less than or equal to t less than or equal to t. So, this is what is called as the risk neutral pricing formula, right. We have seen something similar in discrete time. So, here also you have exactly the same, which is what is the important one. Okay. So, this is what is important one, this is the risk neutral pricing formula. So, we have, how did we arrive at? Just quickly go through once more. We observed that the discounted wealth process is a P tilde martingale, and the martingale property means the middle equation, middle part of this equation, and since we want x t to replicate V t, so this x t is actually equal to V t. Now, if I look at the first and the last second and the last term here, you will see that x t is the wealth that is required at time t to replicate V t, and hence x t must be the price, no arbitrage price of V t at time t, and we call the price to be V t, and hence we get this expression, and hence we get this risk neutral pricing formula that we have here. Okay. So, this is what we have, right, risk neutral pricing formula that we have here, right. This is what is important. Now, given any derivative, what you need to do? You just need to evaluate this expression to get what is the price at time t. Okay. Now, let us see quickly how is this BSM formula for European call option, which we have already said that we gave the BSM PDE along with the terminal and boundary condition, and we said this is the solution, and we did not derive the solution. If you are comfortable with solving PDE, you can solve the PDE along with the boundary and terminal condition and see that that solution actually occurs. What we are going to give now is an alternative using the risk neutral pricing formula, which is what? How do we attempt the BSM formula for the European call option? How do we arrive it? Okay. So, what we have here, call option here. So, my V t is S t minus k positive for some k. So, my V t is actually e tilde of e to the power minus r t minus t V capital T, which I can now write it simply as S t minus k, the positive part given V t. Okay. Now, what we see is that S t, the process is GBM, right. So, S t, which is geometric Brownian motion, is a Markov process. Okay. We can also notice that W t is a Markov process. geometric Brownian motion is also a Markov process, right. So, the right hand side is then is nothing but, okay. So, this implies V t will be some function of t and s t at time t. Because what is this? What is the definition of Markov process? If St is given to be a Markov process, then some function of St, for every function of St, there is another function g such that if that satisfies. So, this is given to be Markov process, because GBM we have already seen, Wt is Markov, this GBM is Markov. So, this is Markov. So, if it is because geometric Brownian motion is a Markov process, so this expression, the right hand side expression, depends on a function of t and st, which we call Ctx, okay, Ctst, right. So, we have to now compute, the program is now to compute Ctx is what we need to do. Now, how do we do? We will use the, now how do we compute this Ctst or Ctx? Because here now if you look at here this Vt expression, you see that S capital T, S subscript capital T, S at the maturity time t and F at small time t, if I look at it, this St is neither measurable with respect to Ft nor independent of Ft, right. So, it is a general condition expectation. Now, in that case, how you will evaluate? You will try to evaluate that you break this St into pieces of at least 2 or more number of random variables. Some of them are measurable with respect to Ft and some of them are independent of Ft, Ft, and then use independence lemma to evaluate the conditional expectation. That is the idea. So, use how to compute is now use independence lemma, okay. So, if you independence lemma if you want to use, now you look at what is my S at capital T. We know S at capital T, right, is nothing but S at small t e to the power sigma w tilde t minus w tilde t plus r minus half sigma square times t minus t, okay. So, note what is this, how do we arrive at this? St is S naught e to the power sigma w tilde t plus r minus half sigma square times t. You take S at t, S at capital T, right. So, what you are taking is S at capital T divided by S at t. So, you will get this expression. This is otherwise you can directly write down also this expression. If you want to obtain from the previous line, you can obtain this, right. So, you can segregate up to t and then remaining portion. This you can see can be written as S at t e to the power minus sigma under root tau times some random variable y, which will define what is it is in a moment, sigma square times tau, okay, where what is this y, which is actually minus times w tilde times t minus w tilde times small t divided by under root t minus t, okay, is standard normal random variable. You can see immediately W capital T is normal, W small t is normal, W tilde small t is normal. So, the difference is normal, right, and the difference has the mean 0 variance t minus t, capital T minus small t. So, if you divide this, you will get the standard normal. If z is standard normal, minus z is also standard normal, and hence y is standard normal, right. And we also use this notation tau for simplicity. Tau is the time to expiration or the remaining time or time to expiry, which is basically t minus t. We denote it by tau because everywhere now tau 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 we will use rather than t minus t is what we will be using it. Okay. So, now once we write ST in this form, now if you look at inside the conditional expectation, the risk neutral pricing formula, you see that you can look at this particular line, you can look at say this particular line expression for this. Now, y is a standard normal random variable which is independent of ft. Okay. So, what you observe is now ST is ft measurable and y is independent of ft. So, you have expressed this capital ST which is neither measurable with respect to ft nor independent of ft as a product of in terms of two random variables. Okay. One is measurable with respect to ft, the other is independent of ft. So, that is what you have done precisely. Now, with this, right. So, this is the y is independent and hence this whole complete thing is also e to the power something something, everything is independent of ft. So, we can now compute Ctx as E tilde by again using the independence formula minus R tau, okay, of this quantity for fixing value of x e to the power minus sigma under root tau y plus R minus half sigma square times tau minus k, the positive part is what then you will end up with. This is the function. Now, we just need to evaluate this function where y is normal 0 1, right. So, we need to evaluate this conditional to obtain the function Ctx. So, this is then nothing but 1 over root pi minus infinity to plus infinity e to the power minus r tau x e to the power minus sigma under root tau some y plus r minus half sigma square times tau minus k, the positive part, and the PDF of standard normal density. So, this is what we have here. Okay. Now, if you look at the integrand, if I look at the integrand now, so if I look at this integrand, okay, so this quantity is positive if and only if my y is less than, say I call this as d minus tau x, which is equal to 1 by sigma times under root tau log of x by k plus r minus half sigma square times tau. So, what you have to do? You just look at this portion and look at when this is positive, which means make the quantity inside the bracket equal greater than 0, and hence you will obtain an expression for y which is less than this, right. So, this is what you will get, this is what you will get. So, if you use this, so if you use this, if this is positive if and only if this is, right. So, this is positive if and only if this is true. So, that means, so that means that my Ctx now is 1 over under root 2 pi minus infinity to d minus of tau and x. Up to that limit I will take, because the other one is 0 anyway. So, I can write this inside one e to the power minus sigma under root tau y plus half sigma square times tau minus k without that positive part. That is what you know you do, dy. Now, this can be further split with this minus. You can split into two part. One is under root of 2 pi minus infinity to, so d minus, for the simplicity I am just using simply x minus x. Now, this e to the power, you can see that this is y square by 2 minus sigma under root tau y minus sigma square tau by 2 times dy minus, okay. So, I will write in this form itself for the time being for this step, minus infinity to d minus e to the power minus r tau, e to the power minus r tau k e to the power minus half y square dy. Remember that the first term e to the power minus r tau, which is outside, and inside the e to the power r plus tau gets cancelled. The remaining terms is what collected here, and this could be written as a perfect square. Okay. So, you can see that this is x by under root 2 pi of minus infinity of d minus e to the power minus half y plus sigma under root 2 pi this square dy minus k e to the power minus r tau of n of d minus of tau x, right. So, slowly we are getting into that. Now, by making a change of variable here, you can write this as x over under root 2 pi minus infinity, this is d minus plus sigma under root tau is e to the power minus some z square by 2 z minus k e to the power minus r tau n of d minus tau x. Okay. And this could be written as x some n of d plus of tau x minus k e to the power minus r tau n of d minus of tau x, with where my d plus of tau x is actually d minus of tau x plus sigma times root tau, which is, you can see, that is equal to this log of x by k plus r plus half sigma square times tau. Look at this previous d minus and d plus, only r plus and here r minus, that is the difference that you have here. Okay. So, this is what is the expression. So, what you have is BSM formula. So, what we have derived is hence the derivation of BSM formula for European call. Okay. Now, see, this is the technique that you have seen, right. How do you derive the European? Now, you have the forward contract price, you have the put price, right. Exactly same process. If you repeat, instead of Vt equal to St minus K, you put appropriate quantity and try to follow the same process, you will be able to derive the price for the corresponding European derivative. So, you can exercise, for example, this quantity. Suppose if this is, so m is some, you can take any real number or m greater than 0. Okay. So, this is exercise, you can try V t equal to S t minus k, sorry, or V t equal to k minus S t plus. For the second two, you already have the expression S t to the power m for some m real number or in general, or m positive in particular. You can obtain what is the expression. Everything, you know, you just have to derive in a similar way, you get the corresponding BSM formula for the corresponding option. So, what we have derived is BSM formula for the European call option, which we have given as a solution earlier. We did not provide how to obtain a solution. So, now we have obtained the solution that we have. Okay. So, we have given the risk neutral pricing formula and we have used it to obtain the solution as how to obtain the exact expressions. So, remember, this is based on the assumption that you can construct a short hedge, and that depends that there is a portfolio process delta t. Now, the existence of delta t is what we need to prove to complete the circle. Otherwise, the risk neutral pricing formula that you are giving has no meaning unless it is accompanied by the short hedge position or at least the proof that there exists such a process. Okay. So, that is what we will do next. Thank you.